This is the subject. It's a joint work of myself and Meir. And it is about locality, determinism. What was it?
There's an equal.
You can? Yeah, we were trying to overcome it. We don't know how to overcome it. It's muted.
Is there a physical way of
Yeah, maybe.
There's got to be a mute box in.
Yeah, but it's muted already.
Yeah, it's muted.
Is it muted?
Can you physically couple the speaker?
I have no idea.
So
Maybe.
it's muted.
Yes, it's muted. It's very strange.
It's a project.
You have an idea how to fix it?
Oh, great.
I told him. Yeah, good. Yeah, I know it's very clearly directly on the.
Well, this is a monastery, so there's a church echo.
Audio. It's not this audio.
But this is about your microphone.
No, that's the mic.
Yeah,
So this is out. So there should be an output.
maybe in the settings somewhere. Maybe I can disable the sound settings. Maybe the microphone should be disabled.
There's also this one. They say here, like that you right-click the speaker icon in the Windows
No,
taskbar.
so I've got the.
Oh, I see. Okay.
Doing all the soft.
Okay, disabled.
Just change the audio input to something that has nothing going in.
Change to projector display. Okay, maybe this.
Does it?
1, 1, 1, 1. Yeah, I think it's okay now. 1, 1, 1. Yeah, maybe this is okay. Okay.
Let's see if there's actual sound.
We're okay.
Okay, it's okay now? Yeah.
I don't hear anything. So.
Yes. Yeah. Okay. So we overcome the technical problem. Hopefully it's the last one. Okay, so I realize that it will be just in a way the other way of the previous talk because I will use mathematics to investigate philosophical concepts. Okay, so okay, so this is the plan of the talk. I will do a short presentation of Bell's locality, the definition of Bell's locality. Then I will introduce a mathematical framework, which is called empirical models and hidden viable models, which was developed by Brandenburgen, Abramsky, and others in the beginning of the century, 2000 and something. And the idea is that this framework allow defining conceptual or philosophical concepts like contextuality, determinism, locality, and others, using very explicit mathematical formulation. And because we have mathematical formulation, we can derive mathematical results, theorems that describe relation between this concept, and then also we can deduce philosophical implication. And then our main contribution will be to add relativity to this framework, which was initially, it doesn't include any reference to relativity, not explicit at least. And then the main result will be to show that relativistic quantum theory is genuinely stochastic, which means there is no deterministic explanation for a theory which is both quantum and relativistic. And of course, I will explain what it means. And then I will return to Bell's locality and consider if it is a good definition for locality in quantum and relativistic theory. Okay, so this is the plan. Awesome. Okay, so let's start with locality, and we have to explain why locality is connected to statistical independence. And the idea, and here are the quotation of Einstein and Bell from their papers about the EPR paradox. Well, they say that locality in this aspect means that if you have measurements which are far away from each other, they should not influence one another, and not influencing means that there will be a statistical independence between the outcomes of this measurement if they are space-like. Okay, and of course it's a little bit more delicate, and we will come to it. But I think Bell maybe should be credited for actually defining a concept like locality, which is a very precise mathematical formulation, which is this one. Now I have to see. Okay. So he say, okay, let's say we have two measurements, A and B, and small letters will denote the outcomes. And let's, in a minute, I will explain about the state space, but he said that usually independence just means that if you have the joint probability of A and B, you actually decompose it to the multiplication of the separate probabilities of measuring A and measuring B. This is the definition of independence in probability theory. But he says something a little bit more complicated, assuming that I have certain state space, or actually it's called hidden variables, but we can call it a state space, lambda. Then he says that we want to have independence, but not plainly as here, but conditioned on the parameter lambda, on the state of the system. So we have in general a joint probability, but he claims that locality means that we can replace this expression with the multiplication of the two probabilities, separate probabilities, conditioned on lambda. If this is satisfied, then the system is local. Okay, this is what appears in Bell's paper. So this is his definition, and now, interestingly, few years before, like I think 8 years before, there is another principle stated by Reichenbach, and this is the principle of common cause. And you say if two variables A and B are positively correlated, i.e. PAB is greater than PA times PB, then either A is the cause of B, B is the cause of A, or A and B are both caused by a third factor lambda. And then you say if, and in the last case, there should exist some other variable lambda, this factor, such that PAB given lambda is equal to this multiplication. And lambda is the common cause. So this is Reichenbach principle of common cause. And in fact, you can prove a theorem. I wrote finite, but it's not necessarily finite. In classic probability space, and I say classic because we will encounter soon non-classic probability theories, that if there are two random variables, whatever, such that PAB is not equal to this multiplication, then there is always exist a random variable such that this condition is satisfied. So in classic probability space, this is guaranteed, okay? And okay, so in fact, I will show in a minute that this is exactly Bell's criteria. Just this is the discrete version. If the Bell's criteria was an integral here, but because we take a finite space, we got a sum. But this is exactly what was written in the previous slide, but discrete version. So in a finite and also infinite classic Kolmogorov, based on Kolmogorov axioms probability space, this is always the case. You could always find this type of lambda. Okay, so this is something that I discovered lately, that Reichenbach posed the same criteria, mathematical criteria, but for common cause, not for locality. This is interesting. Okay, so let's take a very simple example. I will try to avoid the mathematical formula and just show you things with example. It will be much easier to understand, I think. So, very simple example. You have two balls, and red and you have colors red and green, and the probability is that the first ball will be red and the second one green is half, and the other way around is all the other possibilities are zero. And these two variables are dependent, okay? You just make the calculation, 1/2 doesn't equal half times half, so this is dependent. but it is very easy to understand what's going on here. There is simply two states, 0 and 1, each one with probability half. In this state, this is green and this is red. In the other state, this is red and this is green. And given this state, the probability are independent. So I will not go through the details, but if you write the criteria of Bell or of Reichenbach, you see that conditioned on this state, it's independent. It's not independent without the state, but if I introduce this state, so this is like a classic scenario that is very easy to understand. Okay, and this is how this dependence disappears when you introduce the state. Okay, so after this introduction, let's go to the empirical models and hidden variable models framework. It is a static framework. There is no time evolution, just static. It's important to mention. And there is measurement A, B, C, and state space lambda. And the idea is, what is new here, that you cannot measure or you cannot know the values of all the random variables together. You have a certain set of like measurements that you can do together, like simultaneously. Okay? So for example, you can measure only A, B, A, C, and B, C, but you cannot measure A, B, C together. Okay, this start to resemble quantum mechanics because if the operator do not compute, you cannot measure them together. But this is an abstract, no quantum mechanics, no operator, nothing, just abstract setting. Okay, and this, by using this, you can define, as I said, contextuality, strong determinism. I will introduce weak determinism, locality, etc., based on this setting. Let's go to the more details. Okay, so what is an empirical model? And I will give soon some example. Empirical model, as I say, it just list of measurements, A, B, C, etc. And consistent, I will say in a minute what it's consistent. And that you can measure only admissible sequences, like not all the subset of this variable can be measured simultaneously or together, only certain subset. In this example, A, B, A, C, B, C, but not A, B, C together. And of course, you have the probabilities, distributions of this subset, not of all the measurements. Now, consistency just refers to the fact that if I measure A with B or A with C, I want that the marginal probability of receiving A will be the same. Okay? Yeah.
Why are you referring to subsequences? Where's the
sequence? Well, yes, the order is not, no, subsets. Okay, you are right. It should be subset, not subset. You are right. Okay. Okay, what is a hidden variable model? Hidden variable model is like an explanation by state of the empirical model. Empirical model, by the way, is just a table. You can draw, I will show in a minute, you have table, you have on one side the measurement and the outcome, and inside the table you have the probability. That's it. It doesn't refer to anything like real. It's just a table of results of measurement. Hidden variable model, you add the state of the system. You assume there is a system. And now you are getting also the probabilities of the measurement conditioned on lambda. Conditioned for every state, you should be able to compute what are the probability for getting the results. Okay, and what is important, it's the connection with them that a hidden variable model is equivalent to an empirical model if summing over all the state with the right weights, then you'll get actually the same probability that was defined in the empirical model. So in a way, this is an explanation for the empirical model based on certain set of states. Okay. But of course, you want to explain only the ones that you can measure. Okay? This will be important in a minute. Okay, so having defined the framework, we start to define properties. So the first and maybe most important one is contextuality and non-contextuality. And this is a property of an empirical model, not of a hidden variable model. It's important. So non-contextuality is the case where you have this setting, but you can find there is a common probability distribution of all the measurement. Because if you remember, I said that you get distribution only for A, B, AC, and BC. You don't know anything about ABC. If you can somehow find this kind of common probability, that the probabilities that you got are the marginal probability of this one, then this is non-contextual. Okay, this is the definition. And the very basic example, you have three balls, either red or green, and you got this table. Remember, you don't know about all the three of them, only couples. And you got this table, and you want to find a common distribution of all the three of them that explain, or these are the marginal probability of the common distribution. It's very easy. You just see in the picture, you have probability half all of them red, probability half all of them green, and then you can see that very easily that you get exactly this table for the partial measurement. Okay, so this is a standard example. And okay, so what is contextual? And you wonder if anything like this exists, that you cannot find this common probability. And here is a very simple example. Just take the same table, but I move the half to green, red, and red, green, rather than green, green, and red, red. And I claim that you can't find any distribution on all the three colors, all the three balls, that this will be the marginal probability. So how do I know this? It's actually it's very simple claim. If you have three balls and two colors, you will always have at least two balls with the same color, either red or green. You can't have any other way. So you must have positive probability for green, green, or for red, red. Something must be on these two columns, but there is zeros here, which means that whatever you do, you will not be able to find any explanation like this for this table. So this is contextual. Okay, now this, of course, I'm driving to saying that quantum mechanics is contextual, as you know, but this, for example, is something that you cannot imply, you cannot find in quantum mechanics, because this framework goes above or beyond quantum mechanics, and there are scenarios here which in a way you can say, I'm not going to it, but they are more contextual than quantum mechanics, in the sense that Bell's inequality will be more violated than in quantum mechanics. But this topic I will not, just that you know that this is go beyond quantum mechanics. There are scenarios that are more contextual than quantum mechanics. Interesting to ask why, but we will not go into it. Okay, so now we go to properties of hidden variable model, and we want to define strong and weak determinism, which will be useful later. So I just remind you that we are speaking about static definition. There is no time evolution, so it's not that deterministic, is that if I know the state at a certain time, I know what will happen in a different time. Nothing to do with this. The idea of determinism here, that all the probabilities are either 1 or 0. Okay, this is deterministic because we have a stochastic scenario, but if we know for sure what's going on, this is determinism in this aspect. Okay, so strong and hidden variable model is strongly deterministic if the state of the system determine uniquely the outcome of every measurement. Okay, for example, if you look at here, if I know that lambda is 0, then I know that A is 0, and if I measure it with B, it's 0. If I measure it with C, it's also 0. So for every A, B, and C, given lambda, I know exactly only 0 and 1 probability what is the value which is being measured. So no probability for A. Okay, so what is an example of if there is strong determinism, it's obvious, but what is weak determinism? So a hidden variable model is weakly deterministic if the state of the system determines uniquely the outcome of this series or sets that we are measuring, but maybe not the individual measurement. And again, to show that this is possible, look at this table. Again, we have only 1 and 0, so it is deterministic. But if you can notice that, for example, for A, even if I look at lambda equals 0, the value of A is not determined, because here it is 0, see, A is 0, when it is measured with B, but when I measure it with C, it's 1, because the result is 1, 1. So for lambda equals 0, this is 1 times 0, 1 times 1, in contrast to what happened here. So the lambda doesn't tell you individual measurement results. Okay, this is the difference between weak determinism and strong determinism. Oops, what is this? Someone is trying to sell me something here. Okay.
Doesn't show, so no worries. Yeah.
Okay, you don't see it. Okay, good. Okay. So now this is the last properties that we defined. Okay, the first one will be, and this is again for hidden variable models. So the first one, it's called usually parameter independence, but I like more the no signaling term because it's actually say no signaling, and I will explain it. So parameter independent means, and I will just explain the idea, that if you measure A with B or A with C, it doesn't impact the probabilities of the outcome of A. So you don't mind if you measure A with B or A with C. Just the identity of what you measure it with doesn't have an impact on the outcome. So this is called parameter, like B and C are the parameter in a way. Okay, so this is parameter independent. I will explain why it is actually no signaling later. Okay, outcome independence, it's a version of this, but here you want that the outcome of A will not depend on the outcome of B. The outcome of A will not depend on the outcome of C. The difference, it's here, it doesn't depend on the identity of what you measure, B or C, just the measurement. Here, it does not depend on the outcome. Okay, this is the difference. And what is nice is that Bell's locality, the criteria that we see before, actually equivalent to requiring both this criteria. So this, if you have both this property, then this is Bell's locality. Okay, it's possible to show that, and I will return to it at the end, that the formula that we show is actually equivalent to requiring these two properties. Okay, and I think this was revealed in the 1980, not Jarrett and Shimoni, yes, but not under this framework, but they notice that actually Bell's locality is the combination of these two properties. Okay. Okay, so after we have this setting definition, we can prove certain mathematical results. Like for hidden variable model, we can show from the definitions that strong determinism imply weak determinism, and both of them imply outcome independence. strong determinism imply parameter independence or no signaling, and hence strong determinism imply Bell's locality. Okay, because Bell's locality was the combination of outcome independence and parameter independence. So if strong determinism implies both of them, then it implies locality. Now, on the other way, weak determinism plus parameter independence will imply strong determinism. Well, that's mathematical theorem, you can prove them, I will not explain, but And this one, I marked it because it's important. We will use it later on. Okay, for empirical model, first of all, we need to, because we define only contextuality, and if you want to say, for example, what does it mean that empirical model is local? So the definition is that if I find hidden variable model which is equivalent to it, which is local, if I find a local explanation for a theory, then it is local. Okay, because it may have other explanations which are not local, but if I find one local explanation, hidden variable model for an empirical model, then it is considered local. Okay. Now this may sound a little bit surprising. There is an existent theorem. For every empirical model, we can find an equivalent weakly deterministic hidden variable. You can always find weak determinism explanation, and you may think, okay, but I started with promising that I will show that there is no explanation, no deterministic explanation for quantum and relativistic, so how it is possible if here I say that there is always this explanation. So of course I will add some condition. Otherwise I cannot refute this theorem. Okay, and there is another theorem or equivalence theorem that for empirical model, for the theory without the explanation, to be contextual, to have a strong deterministic explanation, and to be local are the same, are the equivalent. Okay, so non-contextual, so I say contextual, non-contextuality, strong determinism, and Bell's locality are actually equivalent. Okay. Conclusion: there are only two types of empirical model in this sense. Either they are classical, which mean, and I say I will define what is non-classical. So classical mean non-contextual, strong deterministics, Bell local. This is the classical Kolmogorov probability that you know. And non-classical, it's just the case where it is contextual, weakly deterministic, and non-Bell's local. And I show you examples that they exist, okay, in the first slide. Okay, so let's see what we have some mathematical result. Let's see some philosophical implication. So again, I remind that there is no time evolution. This is static theory framework. And okay, one point which is important, and I forgot to mention it before, there is a simple algebraic criteria where if you have this table of an empirical model, you can decide if it is contextual and non-contextual. It's complementary, it's not identical to Bell's inequality. It's actually much simpler and it's more general because it's not only for the EPR. Actually, every table, every empirical model, quantum, non-quantum, whatever you want, that you set, you can. There is a algebraic criteria. If I'll have the time, maybe I'll show you how to prove that the EPR experiment is contextual, but not with Bell's inequality, but with this criteria, which is much simpler. But this is only if I have time. So, but it's possible to show that the EPR experiment is contextual. You cannot find a common distribution. Now, quantum mechanics, since EPR is part of quantum mechanics, so it's contextual, weakly deterministic, non-Bell's local. Okay? because if I know it about the EPR is part of quantum mechanics, that's it. So I know that quantum mechanics is from the second type of empirical model. Contextual, deterministic, non-Bell's local. Okay, by the way, yeah.
Do you mean the EPR-Bohm experiment is contextual/non-local?
Yeah, no, I'm not speaking about the original EPR of Einstein. I'm not. Yeah.
I was worried you were claiming.
No, because this is a finite. This is a discrete framework at the moment.
Yes.
Momentum and position are continuous. There are certain ways to extend it, but we'll speak because it's much simpler. We speak about the finite. Okay. So. When I say EPR, I mean okay. So, but the EPR scenario is no signaling. As an EM, we cannot transmit information via the EPR experiment. Probably you know it. So in this framework, I can actually show that this is no signaling, okay? Or parameter, it is not parameter. Okay, like, let's take Schrödinger wave function. This is a state. It can serve as a state for quantum mechanics. And if you know the state, you can compute the probability. If you don't know the state, then you have a table which is averaging over all the state. But this is an example, and this is a stochastic. It's not deterministic, non-Bell's local, and no signaling, hidden variable model, equivalent to QM. When I look at QM, it's just as a result of experiment. Okay. Bohm theory adds to the state also the position. And because you are more refined state, it's become weakly deterministic, and it is non-Bell's local. What is important, it is not parameter independent. So Bell's, these things I will explain later. Bell's theory, in principle, can allow superluminal signaling. And we will explain why actually, how they overcome it. But in principle, weak deterministic allows superluminal signaling. Excuse me? Bohm, what did I say? Bohm. Bohm theory. Okay, Bohm theory. Okay. GRW in this aspect is just as the wave function because it differs only on the dynamic. It doesn't make any impact on the probability distribution. So from this aspect, GRW is the same as Schrödinger. Okay, so now actually we come to our contribution, which is, okay, now we want to consider all this in the framework of relativity. So what we do, we add to each measurement space-time coordinate. Okay, we attach them, and what is more important is we want to define what does it mean Lorentz invariance. Okay, with this is relative. So with Lorentz invariance is a hidden variable model or an empirical model. Is Lorentz invariant in the case that for every assignment of coordinate, we'll have these two conditions. All inertial frame of reference must agree on the probability distribution. This is obvious because we want all inertial frame to agree about the physics. And also we add temporal causality holds in each frame. Okay, we want some causality notion that will be preserved, and it's enough to require it for each frame separately. Okay. Okay, so just to explain, for example, what is mean temporal causality. Temporal causality refers to the fact that if in a frame there is, let's say, a measurement A and then measurement BC that are BC are measured at a time later than A, it can't be the case that whether I measured B or C in the future will impact the result of A. Okay, this is causality. Okay, I cannot just by deciding seeing in the future let's say I'm okay. Maybe here this is a good opportunity to explain this issue of signaling. Let me see. Okay, let's do it here. Okay, why this parameter independent relate to signaling? Imagine that you had Alice here measuring A, and Bob here, space-like, measuring B or C. He can decide. Okay, so what happens that if it was not parameter independent, it means that Bob, by deciding if to measure B or C, never mind what the result are, just by deciding if you measure B or C, can impact the distribution of A, the distribution of the outcome of A, which means that he can actually transmit information from space like instantly, because if he will measure B, you will have one distribution. If you will measure C, we'll have another distribution. So this is a code. You can actually send information from Bob to Alice, and if parameter independence or no signaling is not fulfilled. So this is the connection between parameter independent and remember, it's only by choosing what to measure. It's not, doesn't matter what the outcome is, okay? So this is how you can transmit information, if this is not for me. Okay, let me see, what's possible to signal. Yeah, okay, this is what I explain now. Okay. However, the outcome of A may depend on the outcome of the future measurements B or C, since A, B, or C may be correlated by a common cause. Okay, so I'm not excluding the possibilities that there are correlation between some things that happen now and some things that will happen later in terms of the outcome. But just note that by choosing which measurement to perform, I can impact the distribution, because this will allow signaling. Okay, so this is the point here.
Excuse me.
Yeah.
Just a clarification.
Yeah.
Is it not that if you assume temporal causality, you, by definition, rule out parameter dependence?
Again, can you say it again?
If you assume
Yes.
temporal causality,
Mm-hmm.
maybe I may be wrong, I have the feeling that you rule out by definition the possibility of having parameter dependence.
Okay. Yeah, it's a good question. For empirical model, yes. So from the general table I did, this is what I call consistent for empirical model, but given the state, no. Okay, so they're different. I assume in the construction in the beginning, I defined for empirical models that I want the marginal probability of each measurement to be independent on the other parts of the other measurements. But I'm not saying that this is true, conditioned on the state. And I will give an example, okay? Okay, but it's a good point. Okay. Okay, so now I want to investigate what this Lorentz invariance is what's the impact of it on this framework. So I have a lemma. A Lorentz invariant hidden variable model is parameter independent or no signaling, okay? So it makes sense, because if I require something like this, I'm not surprised that I will exclude signaling. Okay, so let me just explain without going through this. Let's look at the picture here, the drawing here. So you have exactly as I told you, A on one side, B, C on the other side. This is Alice, this is Bob. They are space-like. Because I can attach this should be for every coordinate assignment, there is always a frame. There is a frame where A is measured before BC. Okay, now Lorentz invariance said that the second condition says it is impossible that just by deciding if B of Z is measured, this will impact the outcome of A. This was the second criteria in Lorentz invariant, the causality. You say about causality. We require temporal causality, and temporal causality means that in one frame, only one frame, this frame where A is measured before BC, it is impossible that the identity of which one is measured here will impact A. Okay, and this is exactly the definition of parameter independent. Okay, this is exactly the definition of parameter independence. So in one frame, I show that there is parameter independence. But the first criteria says that all frames should agree about the distribution. So if I prove it to one, then I prove it to all of them. Okay, so that's it. That's the proof. So we know that Lorentz invariants imply parameter dependent or no signaling. Okay, and now this is the main theorem. A contextual empirical model, like quantum mechanics, or EPR, has no equivalent hidden variable model, which is both weakly deterministic and Lorentz invariant. So you can't have weak determinism and Lorentz invariant at the same time. Of course, you cannot have strong determinism because it is contextual, and contextual is equivalent. There is no strong determinism. Proof, okay, imagine that there is such a hidden variable model, then by the lemma it is parameter independent because it Lorentz invariance, and if it is parameter independent and and weakly deterministic, then it's strongly deterministic. This is the sentence the theorem that I ask you to remember. Weak determinism plus parameter independent imply strong determinism. Now, if there is a hidden variable model which is strongly deterministic, then it can't be contextual. Because contextuality means that there is no strong determinism, only weak determinism. Okay, remember, is contextual is weak determinism, classic is strong determinism. Okay, so I have a contradiction with the fact that I assume that this is contextual. Okay, that's it. So we get a contradiction, and this is impossible. Okay, so now the conclusion. There is no deterministic explanation, strong or weak, for relativistic, Lorentz invariant, quantum theory, like Q of T. It must be genuinely stochastic. Okay, so this is the theorem that I promised to prove, and this is the proof. Of course, I added to the framework the Lorentz invariance criteria. Otherwise, as I say before, there is always a weak determinism explanation. But if I require Lorentz invariant, then there is no deterministic explanation. So God must be playing dice. Okay, this is the conclusion. Okay, sorry for Einstein, but okay. Okay, now I can conclude. Maybe I'll do it short. I don't know how much time do I have. What's the time? How? I have 5 minutes. Okay, if I have 5 minutes, okay, that's enough. I don't need more. I have only 2 slides, then we can maybe do the EPR stuff. Okay, so relativistic Bohm and GRW theories. So Bohm theory is strongly deterministic for position because it includes position as a parameter. So of course you know the position, but it is weakly deterministic for example, for spin, as in the EPR. Okay, so it's a little bit more delicate. It depends on what scenario you are looking, and it is not parameter independent because if it was parameter independent and because it is weakly deterministic, it will not be able to explain contextuality. So it cannot be parameter independent, and hence there are states that allows in principle superluminal signaling. For example, if you know the position, you can actually signal in Bohm's theory. Okay, now how they overcome it? They say we cannot prepare the system in this state. Okay, so they exclude preparing the system in certain state, exactly those states that allow superluminal signaling. So you can say it's nice or not, but this is the situation. And okay, it's not Lorentz invariance, of course, because otherwise it was parameter independence. And it follows that weakly deterministic extension of Bohm theory to QFT is impossible unless there is a preferred frame, or that you change it, that it will not be weakly deterministic. But if you want to keep weak determinism, which is the core of Bohm theory, that it is deterministic, then it will not be able to extend it to QFT. Okay? This is quite a strong result. And about GRW theory, I cannot say anything because, as I said, it's just like the wave function. The difference is only, it's not in the static aspect, so I have anything. But there are other claims by, I think, lately from Bassi and Jones, that claim that the collapse structure is not relativistic. Okay, but this is outside of this scope, so I will not speak about it. Okay, now back to Bell's locality. Bell's locality now means that there is an equivalent hidden variable model, which is both parameter independent and outcome independence. And this is equivalent to non-contextuality. And hence, it's the equivalent is a strong deterministic hidden variable model. Therefore, Bell locality definition, this is my claim, tacitly assumes that the empirical model is non-contextual. And this is some kind of a problem because quantum mechanics is contextual. And this implies that quantum mechanics is not Bell's local from the start. Another way to look at it is that Bell defines something that is equivalent to contextuality. So in a way, you can say that this is a redundant definition because, to look at, he defined contextuality. Okay, it's equivalent to contextuality. So you may want to ask, okay, so what is locality? Say, okay, if it's contextual, then it's non-local. But this seems not very nice. Okay, I will refer to it in the next slide. Okay, maybe just something technical. I was trying to find out how it's happened that Bell defined it this way, and it's not explained so much in the paper of 64, but there is another paper of Bell in 1919 which is called La Nouvelle Cousine. You know it? Okay, I'm not sure about where this name came from. Yes, he was in Geneva. Okay, sorry, because it's not related to the content of the paper. And there is something. It's a little bit technical, but just let's go through it quickly. He actually claims that he wants to replace the general probability formula, which is written here, of when how you divide joint probability to the multiplication of conditional probability. This is what probability theory tell you. And here replace it with this one on the left side. And you can notice, I noted it, that here he omitted the big X and here the small x. Okay? So omitting the big X is actually parameter independent because it say, I don't care what you measure together with A. So this is parameter independent. And omitting the small x is outcome independent. Because I say I don't care what you measure, what is the outcome of the other measurement. So there you can find out where you actually make this assumption, but this assumption means that the theory must be non-contextual. And this is a problem if you want to define locality in quantum theory. It's not... Well, I'm sure he was not aware about it because it was many, many years before all this concept of contextuality, etc., were developed. Okay, so the scenario is non-contextual by Bell definition, but QM is contextual. Okay, last slide. Okay, so now what we want to do, if I claim that Bell's locality is not very good for quantum mechanics and relativistic, for example, like quantum field theory. Quantum field theory is also non-Bell's local because it's an extension of quantum, but quantum field theory is considered it is even called local quantum theory. This is how it's appeared. And also there is what is called cluster decomposition principle in QFT, which is, in a way, locality. So it's not very nice that locality of quantum field theory will not be local, or at least by Bell. So what we want is to suggest another definition for locality for a quantum and relativistic theory. And what we say is that we have to keep parameter independence, because this is no signaling. You can't imagine that the theory will allow superluminal signaling, but we want to, we say that requiring simultaneously outcome independence is too strong. So we want to give up outcome independence and say that a relativistic locality of a theory, of contextual theory like quantum mechanics, I will have two conditions. One is a static, only parameter independence, and one is dynamic. I want that the dynamic will be Lorentz invariance. And then quantum mechanics fail the second criteria, so it's not local, but quantum field theory satisfies both, so it is local by this definition, but unfortunately it fails to be Bell's local. Oops, no, that's it. Okay, so basically I'm done. Maybe we'll leave the EPR stuff to the question if you want it. Okay, so that's it. Yeah.
Thank you. Very interesting talk and rich talk. I wanted a clarification about what you said about the non-contextuality tacit assumption in Weltsche.
Yeah, okay.
Because clearly, if this is true, these questions, the relevance of the Bell theorem in its original form for the issue of locality.
Yeah.
Or this is something that Arthur Fine, for example, this was describing.
Yeah.
So I was wondering, so you associate non-contextuality to essentially to the existence of a joint probability distribution, no matter whether the observable are compatible or not.
Yes, exactly.
But it is not, if you assume locality, you restrict the distribution that are relevant. So locality is in some sense neutralizes the joint probability assumptions, so that in this sense, if you assume locality, you don't need to assume a joint probability condition. So it is
No, it's implied. What I show is mathematically, as soon as you require locality in the Bell sense, it's implied that the theory will be non-contextual. This is mathematically equivalent. I can prove that once you require parameter independent and outcome independent, or Bell's formula, it doesn't matter, they are the same. As soon as that you require this, you can't have contextuality mathematically. See, it's not something that you can avoid. Mathematically, these two concepts are equivalent. Okay. Now again, I say Bell's didn't. I think the terms contextuality was not developed there, was not discovered there anymore. But so he was not aware of it. But he defined locality when only I think people there believe that the probability in quantum mechanics is the same as Kolmogorov. Only later, maybe Pitovsky had a lot of contribution to this, people start to realize that this is a different theory of probability. And this framework actually make it more explicit. Say, okay, I'll explain you exactly when it is contextual, when it is in non-contextual. Okay? So this is the claim. Okay.
Is it a follow-up?
I would like to respond to that.
Then it's your turn.
Okay.
So in my view, locality, how do I express this in English? I agree that you need non-contextuality to define locality in that sense.
Okay.
But I believe that Bell used the spatial separation as a motive to presume that whatever model I put should be local.
Yeah, okay.
Sorry, that he used locality to presume that whatever model I put should be non-contextual. So this is why it's contained.
Okay.
So
Yeah.
locality does contain the assumption of non-contextuality.
Okay.
It's not like Bell did not know about this.
Okay,
He
maybe,
used,
yeah.
He uses spatial separation as a motive for the
Okay.
non-contextuality assumption.
Yeah.
That's my way.
Okay. Yeah, again, I'm not sure if these terms of contextuality and non-contextuality were known at his time. I'm super. If you know historically.
The concept occurs in Coates and Specker's paper in 1960.
1960. Okay. What, contextuality and non-contextuality? Okay, interesting. So I was not aware about it. So you mean that Bell was aware and actually deliberately?
This is unclear to me. I believe.
Okay.
I would think that this is the case, but I'm not.
Yeah. Okay. So it's interesting historically what was going on.
We also had in 73 the distinction between contextual and non-contextual hidden variables theories was printed. Was
Yes.
shown.
Yeah. I'm sure he was a.
73 later.
Yeah.
This is,
Yeah, in the 1990 paper, I'm sure it was already known, but the 64, I'm
the
not sure.
comparison that I make now is actually present in a paper by David Meir in 1990. So
Okay.
the sort of statement that
Okay.
locality is really a motivation for the non-contextual.
Okay. So when it's, I cannot argue with the definition. I'm just saying that. Exactly. And I say for a quantum and relativistic theory, Bell's locality is not very good because QFT. I want QFT to be local. It's a matter of taste, yes. Okay.
Yeah, but the words have different meaning.
Yes. Okay.
When you say local quantum theory, you mean something else than Bell locality.
No, I think that the cluster decomposition principle theorem is actually a kind of locality. It says that if...
I'm not disputing that.
Yeah,
It's
okay.
just that the formal meaning is
Yes,
different.
okay.
I agree with Jan. Bell's motivation, and at the end of the 1966 paper, in which he criticizes Coates and Specker for Neumann and so on.
That's right.
A better motivation should be for these results should be in terms of locality conditions.
And he wrote the 66 paper before.
Before the
64.
Yes.
Yeah. Okay.
That's right. So we did that.
Wonderful
Okay.
paper. I hope you have something to create already so that I can follow. You published that? Okay, great. I was wondering whether the fact that you can have action at a distance in Bohm's formulation, that is, if you move this around, you immediately
Yes.
you're going to influence that. But of course, that's not sufficient to determine which privileged inertial frame is involved. But it seems to me that if you have action at a distance, you have a reason to believe that you are working in a non-relativistic setting. Which of course is not what we want, because I agree with that.
I wanted to be careful, so I don't want to say that there is no way you can extend the Bohm theory to QFT. But what I'm saying, it's going to be very difficult because you have to give up something. Either weak determinism, or you want to have a preferred frame, or.
Of course, from the fact that you can signal at this, you can have this action at a distance is not sufficient claim that you can signal.
No. In Bohm's theory, I can show it later. I will show you that even in the EPR experiment, I will show you that I can signal faster than the speed of light, mathematically.
So transferring information.
Yes. If you can create this state, provided you control. Exactly. No. Yes, but in general, this is general result. If you have a weakly deterministic theory, you can signal faster. And I will show you a table, and I will show you a state where you can actually signal faster than the speed of light. Okay? Now you say, okay, maybe you can't prepare this state. You cannot. You cannot prepare the state for some external condition, but if you can prepare the state, I will show you that I can signal. Okay? So I'll do it later. Let's do it later.
So we have 3 more questions.
Okay.
There are so many problems when we try to quantize even just things like photons. Because there is kind of some non-locality built in. And that what you're describing might be the reason for why we have a difference between fields and particles. For example, if I want to create a local electric field excitation, I need to have particles everywhere. Or think of a mass. If I want to have a gravitational field that is really spiky, then I have to have masses everywhere. Or if I have a local mass, then I have fields everywhere. And that might be a way of breaking the locality, because I guess the moment you break locality, even just a tiny bit, then relativity and quantum might go together again. Maybe this is some of the reasons of why we have these non-local fields that make so much trouble how to incorporate them.
I think that in QFT what they say that you have non-local field, non-local particle, you have local interactions. The idea is that interactions are always local, but fields or particles cannot be local. So it requires what is important for you to be local. And it happens that...
When you change things locally, you also change the fields.
Not locally, exactly, Okay.
So I wanted to thank you, Avi, that was really interesting. I wanted to ask you about the one precedent that you mentioned to Bell's locality, which is Reichenbach's principle of the common cause. I didn't see it playing any role in the rest of the talk.
I just wanted to show that this is exactly the same definition, but Reichenbach used it for a common cause, and Bell used it for locality. I didn't comment on it. Historically, it's interesting. I don't know where.
It's worth remarking that there is a large literature after Reichenbach exploring common cause models that we not find. They're called non-screening of common causes. And there is a very large literature establishing conditions for when those obtained while failing relevant locality conditions. And I'm just wondering, these literatures, they seem to have developed in separate kind of bubbles. And I'm just wondering, did Bell know about Reichenbach?
It's a good question. I don't know. I actually noticed it. This slide I added very lately. I don't know where I read it. And I saw Reichenbach criteria. And I say, it's the same. I didn't notice it before.
Formally, it's identical.
Yes, it's identical, but from a different philosophical concept. So
It was Van Frassen who used that. Yes.
But that was well after Bell. So what I'm wondering is, because it's a one historical precedent, so I'm curious, did Bell read Reichenbach or any of the literature on causation that was employed in this condition?
I didn't follow it up. I must admit, I didn't follow it up.
So we have a direct follow-up, Gemma, right?
In case that could be interesting to anyone, there's a program led by from Speckham, Brunner, and many people, right, who are presented trying to put together these ideas of causality
and locality.
Locality.
Okay.
So last question.
This is a comment, really. I think you're right to say that QFT is local, but obviously fails to satisfy Bell's locality. But interestingly, in Louvain, Bell claimed to be able to derive Bell locality from the causal constraints of relativity. And I believe Bell was, I don't say it lightly, but I believe Bell was wrong
Okay. Yes. I'm happy that someone else said it, not me.
I'm writing a paper sort of criticizing.
Yes, good. Okay, so.
You have to have a permanent position.
Okay. Okay. Okay.
Thank you very much.
Thank you. Bye.